Okay, for question one, I thought we'd look at something that's a little bit different than our normal structures. This is Ritalin on the right, or Vocalin, which is a stereoisomer of Ritalin. Generally, this is the one that's used for children because amphetamines are thought to cause both developmental and growth problems. So, generally not recommended unless the case is very severe, aside from the, other various problems that amphetamines cause. In case you didn't know this, Adderall is an amphetamine. It's not methamphetamine, but it is an amphetamine. So similar mechanism of action, similar side effects, similar problems. In instant release version, similar problems with addiction. Not quite as bad as meth, but close. Okay, so this is preferred. A little bit milder, a little bit safer, a little bit less effective, depending on the case. So, since one of the stereoisomers is useful compared to the other three possible diastereomers of Vocalin, the compound on the far right, then it's useful to be able to make just that one. And if we start from the precursor on the left here, that's relatively straightforward. It's just a simple hydroboration to put an oxygen in the right place, and then removing a protecting group, oxidizing that alcohol up to the acid and making an ester. These are relatively simple things, some of which we haven't covered this semester, but the reactions that are not shown under that multiple steps label are very simple, very close to foolproof. The hard part here is what we're talking about in this particular case is an alkene reaction. First, somebody has to make the right alkene with the right stereochemistry on the amine. Well, somebody took care of that before we got to this question. Second, the hydroboration actually takes care of the rest of it for us. So, two parts of the question here. One, mechanism for the hydroboration. You can ignore the BOC group, the BOC group, is a nitrogen protecting group. It does not do anything chemically here. When we talk about stereochemistry in part B of the question, it just plays the role of being really, really big, and that's important. But in terms of mechanism, no role at all. So let's take a look. So we're down to just this, and we're going to make it even simpler than that, in that we're just going to basically abbreviate the alkene. So what I mean by that is we don't care what the groups are, as long as we know that they're an unsymmetrical alkene. As it turns out, in this case, we have an aromatic ring. We have an aromatic ring attached to one of the alkene carbons here, so that's going to basically up our normal regiochemical preferences quite a lot. So this might be very close to 100 to 0 in terms of regiochemistry. So the actual hydroboration is a simultaneous addition of this, so that we have basically an attack by a more negatively charged hydrogen simultaneously with an attack by the remaining alkene pi bond, and the third is the loss of that hydrogen from the boron. So the preference is, of course, which side is more cationic, and that's going to be generally hyperconjugation, the more substituted one, but in this case we also have a resonance issue. So if I had just this, the simplest possible alkene with an aromatic ring on it, if I drew a resonance structure for that, this is much more reasonable, because it has a cation in a place where it's available for resonance. So the cation would be stabilized more on this position than this one. So one of these R groups is an aromatic ring. So that's going to basically give it the same type of stabilization here. So we've got a very good reason why a negatively charged hydrogen would be attracted to the carbon on the left in the alkene. So mechanistically, we end up here. We have now a hydrogen and a BH2 group on the same spots where the alkene was. This basically goes 2 more times. You don't have to draw that. So that we're basically looking at, I'm going to abbreviate a lot of this right now, just to make my life a little bit easier. So we're going to end up with this eventually. We're going to end up with three different, I don't know, we'll put a double prime here, three different, so that's going to be this entire section. Three of these attached to the boron, one for each of the original hydrogens on the BH3 group. So we end up with a trialkyl borane. Again, you didn't have to draw that part. The first one is the only one that really matters in terms of setting up the regiochemistry, which is what we care about for part A of this question. All right, so that's the first step of the mechanism. So the second step is this. We have the hydrogen peroxide and hydroxide. And that together combine to give us the hydroperoxide anion. So we have this. The boron is sp2 hybridized, it's trigonal planar. It has an empty orbital. Now, when we get the reagent, that's taken up temporarily by the solvent. That's what the THF is for in the original scheme here. That's what this THF molecule is for, is just to take up that orbital temporarily. But in solution, that is a what's called a dative process, an on and off coordination process. So we can assume it's not there if there's a reaction that's possible. So in this case, we've got an anion, much better nucleophile than any solvent is going to be. So that's going to get us here, where now we have this. It's tetrahedral. I'm just going to draw it as if it's flat for the moment, just to make life a little simpler. And I now have a negative charge here. So what occurs next is a rearrangement. And that is one of the R groups is going to shift downward to the oxygen, but it's taking its pair of electrons with it. Then that's going to displace hydroxide. So what I'm going to get is this. The boron goes back to being neutral again. So it loses the fourth connection. Now it's back down to 3. One of those R groups is now moved one atom further away and is attached now to the oxygen, what was the hydrogen peroxide anion, the hydroperoxide anion, and I get another molecule of hydroxide as a leftover. So that, just like the hydroboration, will happen again here and happen again here. So again, you did not have to draw everything happening 3 times. So we're here. The bond, not a radical. So we eventually get to this, the trialkyl boronate. Now, generally speaking, what happens then is at the end of the reaction, we add acid and water. Even just water you could do to explain this, but acid is a little simpler to do. So we're going to have, we're going to have water here to act as a nucleophile. We're also going to have a slightly acidic medium to protonate the oxygens. This is a metalloid, but we can look at it as behaving covalently when we need it to, which is basically most of this reaction, and then think that it's kind of ionic as well, which means we could sort of treat it more like this, you know, in explaining what happens at the very end, which is we end up adding an H plus to the oxygen, give us an alcohol, and then leftovers go to the boron. That's kind of the overall scheme of it, is we end up with the borons attached to OHs and the alcohols attached to a hydrogen. So essentially we're adding water across this bond overall. So it's up to you which way you want to draw this. More likely, because of the metallic character here, we're going to see protonation happen first. So this is aqueous acid. So we're looking at protonation, probably the first step. And so all this is going to happen more than once, but we only need to draw one of them. So we have this. We have this, and it's protonated. So either water is a nucleophile or hydroxide is a nucleophile in the previous step. more likely water is a nucleophile here, is going to come in there, and that's going to give us an overcharged boron again. So that we're going to have this, which can be neutralized because it's now got 2 cations on it. That's not necessarily very realistic. It may be a better idea to have drawn the nucleophilic attack and a neutralization first. The order is not critical because they are all happening in equilibrium simultaneously. But if I did that, I'm here with now an OH group, 2 OR groups, and I also have a negative charge on the boron again because I now have 4 bonds to it. So now I have this, and because I now have opposing charges, I have a justification for it to go, which is that. So if that happens, I'm going to end up, so each one of those is going to get replaced with an OH group on the boron. So what I'm going to have is this as my leftovers, or the right structure is this, that I now have a phenyl group, sorry. So I now have the phenyl group up here. I have the stereochemistry set on that nitrogen. And this was a 6-membered ring. And then I have an oxygen. My new hydrogen is back here. And I have an oxygen with no stereochemical definition. So this is what ROH actually is. R double prime OH here. So that's mechanistically what I need to see. The order on those last couple of steps really isn't critical. More likely we're going to have a nucleophile neutralized before we end up creating an intermediate with 2 charges on it. That's a little bit unrealistic, but I wouldn't mark it wrong because it's a matter of just doing the steps in an opposite order. Doesn't really matter. Okay, so that's part A of the question. Part B of the question is, how do I end up with this particular stereoisomer? So let's go back and look at the master structure here. Specifically, I ended up with the aromatic ring upwards from its original position. The attack of the hydride then had to be on the other face of what was the alkene. And that shouldn't be a real surprise. The hydroboration, because of how it works, the boron has to come in either above or below. The boron and the hydrogen, adding simultaneously, have to come in either above or below the plane of that alkene. So, as drawn here with this nitrogen upwards and probably restricted rotation, which means I'm going to have this very big group kind of locked to what I've drawn here as the top face or sticking out of the board. The better approach then is for the hydrogen and the boron to come in from behind the board or behind the screen that you're seeing now. If that happens, what it's going to do when that pi bond breaks is it's going to drive the aromatic ring as that comes in. So as we're showing this going backwards now, the hydrogen going backwards, what's happening is the aromatic ring is going forwards. It's pushing the aromatic ring into the stereochemistry that we actually see eventually. So I can just draw it as the intermediate stage here, but doesn't matter what this is now. But so if that hydrogen is forced to the other face, it's going to set the stereochemistry of that carbon where the aromatic ring is attached. And that's exactly what we're getting at here, is that a large group on one face forces the attack on the alkene to happen from the other face. This is different than just taking a reaction on a planar functional group. This is still a planar functional group, but it's not a planar molecule. So the approach to each side of that alkene is not identical, and in fact is very preferential to this particular one face attack, giving us basically only one stereoisomer when it's over. That was the entire point of this synthesis, was that once one stereoisomer was proven to be more useful, then somebody has to make it selectively. Instead of saying, okay, I can make all 4 possibilities and then find some deity to pray to that's going to let me get one of them out cleanly. It's not going to happen. Diastereomers, you can separate them hypothetically. It's not trivial. And you have 4 diastereomers, but that's 2 pairs of enantiomers. So even if you get the diastereomers apart, what would be trans here instead of the cis arrangement of the nitrogen and the aromatic ring, you still have a pair of enantiomers. Getting all that apart cleanly is not trivial, and it is time and labor intensive. You don't want to do it. So if you can make one of them cleanly, instead of having to try and clean up a mess afterwards, then that's very preferential. And that was the point of this synthesis. That's why one of the stereoisomers, one of the stereocenters is already set in our precursor, is to control the stereochemistry of the alkene addition, and therefore control that you're getting basically only one diastereomer out of it.